Hello and welcome back. Today we're going to be talking about the Cope rearrangement. The Cope rearrangement, shown here, is a kind of 3-3 sigmatropic rearrangement that involves a diradical-like transition state. Now initially I was going to include the Claisen rearrangement as well, but that turned out to be a little bit long, so I'll discuss Claisen rearrangements later down the road. Now when considering rearrangements involving two allyl radicals, the transition state could adopt either a chair or a boat conformation. So we're going to consider both. But before we do that, here's the frontier molecular orbital theory underpinning the rearrangement. So in terms of the reaction itself, we have two linked olefins joined by these two atoms X and Y. The bond between them is highlighted in red, showing that this is the bond that's going to break. So when we apply energy to this molecule, we enter this transition state, which is pericyclic in nature. So the two double bonds, the bond that's going to break, the bond that's going to form, these are all in flux, with this breaking bond donating one electron apiece to each half of the intermediate. These bonds reform over here. Now our double bonds are associated with the atoms X and Y, and we have our new bond formed over here, highlighted in blue. Now considering looking at our transition state, we have two 3-atom halves, so 1, 2, 3, 1, 2, 3. And because we're considering them to be radical species, there's going to be 3 electrons in each of their pi systems. So for a 3-atom species, we can start with bonding orbitals, then we have a non-bonding orbital, and then finally we have an anti-bonding orbital. If each of these orbitals can only hold 2 electrons apiece, and we have 3 electrons to deal out, 2 are going to go into the bonding orbital, and then 1 is going to go into this non-bonding orbital here. So the highest occupied molecular orbital is going to be this psi2 orbital, highlighted by the red box. Still focusing in on this transition state, if we consider it 2 3-atom allylic radicals, and the highest occupied molecular orbital places the pi orbitals in this configuration shown here, there are 2 ways that we can stack them together so that these breaking and forming bonds interact with one another. We can orient the 2 3-atom species in this way. So if we draw it all together, that gives us this chair conformation. Or we can draw these 3-atom species as kind of overlapping, which gives us this boat conformation shown over here. These are the 2 conformations whereby you can get synchronous bonding between all the pi orbitals, so essentially getting this delocalized state of the intermediate. The outermost p orbitals need to align in a constructive manner. So this introduction would be the same for both Cope or Claisen rearrangements, given they both undergo this 3-3 sigmatropic process with this transition state shown here. The main difference between Cope and Claisen is that for Cope, X and Y are going to be carbons, whereas for Claisen, either X or Y is going to be an oxygen. But moving forward, given today's all about the Cope rearrangement, X and Y will be carbons, and we'll be adding different functional groups all around this basic scaffold shown here. So if we're going to consider both the chair and the boat conformations when we think about the transition state, it's worth knowing a little bit about them. So the first thing to say is that they've measured the relative energies of these 2 transition states and definitively shown that for simple systems, chair is lower in energy than boat. And we can take a look at the original paper, or in some of the first experiments were done. You can see that when they draw out the chair conformation, any functional groups attached to our allylic groups have a lower chance of sterically interfering with one another. So here where the bonds are forming and breaking, any R groups are going to either be in the axial or the equatorial positions. And particularly those in the equatorial positions are going to minimally interfere with the transition state. If we now take a look at the boat transition state shown down here, you can see that there's a lot more interaction between the 2 allylic halves coming together to form the products. If we have any functional groups attached to the allylic groups, there's a much higher chance that they're going to sterically interfere with one another. So for me, that's the likeliest origin as to why you have this higher barrier to activation for the boat conformation. And indeed, you can look up the reaction energetics and looking at the 2 pathways that this central molecule can take to form the product either by chair conformation or the boat conformation, we can see that the energy barrier going via the chair conformation is significantly lower than going via the boat conformation. And given that these are thermally driven rearrangement processes, the reaction is going to proceed via the lower activation barrier to get towards the products. So considering this reaction down here, it is much more likely that our starting material is going to progress by the right-hand pathway, proceeding through this chair intermediate. And the key experiments that were done to prove this were the Doering-Roth experiments. These very elegantly utilise sterics to look at how the orientation of methyl groups would influence the stereoselectivity of the products of the rearrangement that were seen. So specifically, these methyl groups would either favour or disfavour the boat and chair transition states. And by harnessing different diastereos, it might be possible to select the major products that you see at the end of the reaction. So looking first at the threoisomer, one methyl group oriented towards us, the other methyl group oriented away from us, and we can draw out the reactions as they would proceed if the starting material was oriented according to the different possible transition states. So the topmost reaction is going to occur via a chair transition state, where the bond to be formed is this dashed line here. So we can draw out basically the chair transition state and map out the location of all of our functional groups within it. Once we've done that, we can redraw it, having broken the bond, formed the new bond, and shifted the two double bonds to be adjacent to our two methyl groups, essentially the way that we know the Cope rearrangement will proceed. And having done that, we can look at our product and see what kind of olefins we have formed. And for the top example, we can see that on this side of the molecule, we have a trans olefin, and on the other side of the molecule, we also have a trans olefin. So this is a trans-trans form of the product, drawn out simply over here, and this product was seen with 90% yield. The next reaction we consider is also going to go via a chair transition state, but we're going to swap the location of the methyl groups. So for the top example, we can see that we have the hydrogens in the axial positions, while the methyl groups, these are in the equatorial positions. And we would predict that this is going to be the lowest energy transition state, simply because there's not going to be any steric issues with having our two methyl groups in the equatorial positions. However, this time we've swapped around our chair transition state. Now our methyl groups are in the axial positions and our hydrogens are in the equatorial positions. This is going to be a little bit more sterically demanding, so our prediction would be that we would see less product compared to the first reaction pathway. So indeed, we have drawn out our starting materials according to our new chair transition state. Next, we break the bond and form the bond and shift our double bonds, how we know that a Cope rearrangement would occur, and that gives us this new product shown over here. Now, if we look at our olefins, we can see that it's in a cis conformation on this side of the molecule, and indeed is also in a cis conformation on the other side of the molecule. So we've gone from trans-trans, shown here, to a cis-cis configuration of the product, still going by a chair transition state. And indeed, the ratio of these two products is 9:1, so 90% trans-trans, 10% cis-cis. Effectively, that's all the products that we're going to see in the reaction. However, we can also draw out our final reaction pathway. This one's going to proceed via the boat transition state. So we draw out our starting material. We can see that potentially there's going to be steric issues all over the place. But if we react our starting material and draw out our product, breaking our bond and forming our new bond, shifting our double bonds towards the methyl groups, what we get at the end is one trans olefin and one cis olefin. So we get a trans-cis product. And we see less than 1% of this product. Effectively, none gets made at all. Just as a reminder, looking at the original paper, we can see that this transition state is going to be a lot more strained, sterically congested, compared with the chair transition state. And that is indeed borne out in the ratio of the products that you see. So that was for the threoisomer. What about for the mesoisomer? So now we have our two methyl groups. They are on the same side. They're either both going away from us or both coming towards us. Doesn't really matter because you can rotate it by 180 degrees and create the other one. And indeed, because they are both equivalent, now there is only one chair transition state that we need to consider. So we can draw it out. We have one hydrogen in the equatorial position, one methyl group in the equatorial position, one methyl in the axial position, one hydrogen in the axial position. And if we flip around our chair to create the other version of the chair like we saw in the previous slide, we're just going to recreate this same molecule again, where the methyl group is here and the hydrogen is here and the methyl group is here. It's equivalent. And when the reaction proceeds, what we do is we create one cis olefin here, one trans olefin here. That gives us this trans cis product, and we see that in greater than 99% yield. The only other option we could consider is going by a boat transition state. We draw that out. It has all the same issues that we saw in the previous slide. What we get is one trans olefin and another trans olefin, so we get a trans-trans product, and we see that product in less than 1% yield. So effectively, we don't see it at all. Probably the last thing to say about this slide is, while we've shown that the chair transition state is vastly favoured in these experiments, if you had a starting material that for some reason it had a selection of functional groups that prevented the reaction from adopting the chair transition state, meaning only the boat transition state was possible, the reaction may proceed by that pathway. However, most of the time, the activation energy of going by the boat transition state is going to be a lot higher than going by the chair transition state. So it's going to be very rare that you see products from that pathway. So what are some useful coping strategies? Well, you can implement ring strain into your reaction, specifically destabilizing the bond that's going to break during the Cope rearrangement. If you do that, this is going to drive the reaction forwards, basically accelerating the reaction, or allowing it to be performed at lower temperatures. What it's going to result in is this expanded ring system that experiences less strain than our starting material would. So again, we can imagine this as an equilibrium. If you have a ring strain component that gets alleviated, the equilibrium is going to shift towards the side wherein that strain is alleviated. Here's a couple of examples where you can harness ring strain to influence the equilibrium. Here we have our starting material. It has a highly strained 3-membered ring. Apply some heat, Cope rearrangement occurs, and we get a new bicyclic system, only now our 3-membered ring is gone and we have a 4-membered ring. Strain still experienced by the molecule, but less than having this strained 3-membered ring. Another example over here, we have a 10-membered cyclic system. You might not think that that looks particularly strained, but we do have 2 trans olefins within the cyclic system, so there's not that much conformational flexibility within this molecule. So because of that, when we heat it up, we get our Cope rearrangement. It forms a new 6-membered ring with 2 attached olefins. We can see the stereochemistry is quite interesting. This comes back to the overlap of the orbitals, considering frontier molecular orbital theory, and the way that the 2 allylic radical-like 3-atom species need to sit atop one another in order to achieve that synchronous state where all the bonds and the orbitals are delocalized, going through the transition state. Now, there are also other factors that should be considered, which can drive the equilibrium back in the other direction, i.e. towards more strained products. And one of those factors is tautomerism. So here, let's look at this new molecule shown here. It's quite similar to this molecule shown on the right. Main difference is now we have this alcohol group adjacent to the bond that is going to be breaking. If we drive this reaction in this direction to give us this product, so we've gone from an unstrained 6-membered ring to a strained 10-membered cyclic system. So this is not what we would initially predict would be favoured to form. However, the addition of this alcohol group adjacent to our double bond means that we've created a system that can undergo keto-enol tautomerism. So given the main source of the strain in our 10-membered ring system here is the 2 trans olefins, if one of our trans olefins can undergo keto-enol tautomerism, forming this species down here, a ketone, now the ring has alleviated its strain, pushing the equilibrium over to this side of the reaction. Essentially, it follows the rules, but you have to consider a subsequent step after you form the more strained cyclic system. Last thing to talk about is accelerated rearrangements, or the Oxy-Cope style of reaction. In the previous slide, we had an alcohol adjacent to our bond that was due to break. If you are to deprotonate that alcohol, creating an alkoxy substituent, this greatly increases the rate of reaction for the Cope rearrangement by several orders of magnitude. So where previously you needed to use a large amount of thermal energy to drive the reaction forwards, you can do those same reactions by the addition of base, sometimes at very low temperatures. And similarly, reactions that would take days now occur in seconds. Now, the way that you form this alkoxy substituent actually does affect how much the rearrangement is accelerated, with potassium alkoxy substituents typically delivering the best results, followed by sodium, followed by lithium. Although lithium can be useful for imparting stereoselectivity into Oxy-Cope reactions. So here's a couple of quick examples of Oxy-Cope rearrangements. We have our starting material shown here. We add our potassium hydride, forming our potassium alkoxide. Rearrangement then occurs. This bond breaks. New bond forms here. Double bonds shift over to this position, giving us this product shown here. If we work this up with acid, once again we have a situation where ketoenol tautomerism is going to be a factor, and we wind up with this ketone product shown here. Second example shown down here. Once more, we're going to add our potassium hydride, create our potassium alkoxide. This time, we even have some ring strain in here that is going to drive the rearrangement forwards. We break our red bond, form our blue bond over here, shift our double bonds across. Once again, ketoenol tautomerism is possible, and we're going to wind up with this ketone product over here. Biggest difference for these reactions compared to the previous ones is that these reactions would proceed under relatively mild conditions, whereas the traditional Cope rearrangement requires large amounts of heat to proceed. So one of the big benefits of the Oxy-Cope rearrangements is that it's tolerant of many more functional groups that would degrade under the forcing conditions you usually need for a Cope rearrangement to proceed. So that's it for Cope rearrangements. Traditionally, it's a thermally driven 3,3 sigmatropic rearrangement, wherein you get carbon-carbon bonds formed and you get excellent atom economy in your reaction. You can harness ring strain to drive the rearrangement process forwards and influence the equilibrium of the products that you see. Later, there was development of the Oxy-Cope variants of the reaction, and these did away with the need for really high temperatures by substituting in a base to form an alkoxy species. Given you had that alkoxy functional group, typically adjacent to a double bond, this gives you ketoenol tautomerism, which is another way of influencing the equilibrium of the products that you see. That's it for today. Thanks for watching.